I introduce just vector space. Let's think about 3 by 3 matrix. Let's call them M. This first question, does it form a vector space? Let's say this is 3 by 3 matrix. Okay. Up to now, we will say, oh, 3 by 3, no problem. I see this V1, V2, V3. So I represent them as a collection of 3 column vectors, right? Or another view is, I can see this is row 1, row 2, row 3. I can see as a collection of 3 row vectors. Another view is, can I see as this is just one vector with 9 dimensions? Instead of just, let's say, whatever V1 to V9, I rather represent them as V1, V2, V3, V4, V5, V6, V7, V8, V9. This is more or less vector notation for this, but this is more or less matrix notation for the same one vector, right? Can you see that? Okay. Let's say I took a picture of Ehabin, right? This is Ehabin. I took a picture of you. So pixel is 124. This is 1 million pixel, right? 1 megapixel, right? This is number of dimension, right? So if I can see this as vector, what's the dimension of this vector? This dimension is R 124 times 124, right? This number of dimension, right? Let's say this is Ehabin's picture at age 19. Okay, I have another picture, is Ehabin's picture at 60. This is another dimension R24 and R24, right? I have only 2 pictures. I try to find out what's his picture, let's say 40. Can I just add them up, just make average? Kim Sang-ho, can I just take 2? Basically, this no problem. This is, let's say, V1, this is V2. I says, this at the picture is V1 is V2. His picture at 55, I says, in that case, actually, is V1, 0.1 V2, then there's 0.9 V2. Assuming your face changes linearly, right? Basically, this is what we are treating them as a vector. We are combining them linearly, right? Just linear combination, right? So it means, I can see them as this is a subspace. We can add vectors, right? Then we can multiply scalar. We can combine them. So we can say for this vector, I can see as, so even just a 3 by 3 matrix, I can see them as a 9-dimensional vector space, okay? So in the case of pictures of 124, 124, right? How about color picture? Let's say this is black and white pictures. How about colors? what's the dimension of color pictures? 박한솔, what's the dimension of color pictures? Just think about it. So this is number of pixels, right? We have 3 colors, right? 3 times, right? RGB, right? So this is number of dimensions, or number 2. So when you see what's the possible set of values, this is values, right? Okay? Combination. Okay. This is our line. Then I said, so okay, 3 by 3 matrix. I call them M. I say, okay, dimension seems to be 9. Can you find the basis? Nine dimension, you need 9 bases, right? Can you find them? Kim Myung-jin, can you find the basis for this? How about this one? 1, 0, 0, then 0, 0, 0, whatever, then start. Oh, just go to 0, 0, 1. Okay? It's 9 of them, right? So you can combine them linearly, then it becomes the whole space, right? So that's the one you can find the 9 bases, right? So from that, we found out what's the dimension, what's the basis, right? What's the all upper triangular matrix for 3 by 3? Let's say matrix is like whatever. Oh, this one non-zero, whatever values here is all 0. What's the dimension of this? Is upper triangular matrix, right? What's the dimension of U? Park Chang-ho, what's the dimension of U? Speak up. 잘 안 들려. 예? No. I treat this one as a one matrix, okay? That's why. Up to now, that's why I'm asking you. I just said this A 3 by 3 matrix. Once I can see view it as matrix, that's one view, right? Another view is, oh, I can see as this is 3 vectors. Okay? There's a V1, V2, V3. This is another view, right? Okay? This another view is, oh, I rather view this way. This is another view. Okay? Now I have very different view. Oh, I just see this as just one vector. Not necessarily vector. Just one vector. Okay? Then one vector. Oh, I have one vector. Then how many components in that vector? 지영탁. 9 components, right? Oh, this is 9 components. Okay? Whatever component, right? Then all cases are aligned. Each one has a real value, right? Oh, this is 9-dimensional space. Okay, that's a logic. Then, oh, how can I find the basis? Okay, this one. Oh, that's this first one. The last one is whatever. So we just have 9 of them. Okay? That's a logic. Okay, in this case, I just see this as a vector, okay? Okay? just forget about this. Then I say, oh, how about this upper triangular? Upper triangular, the parameter is always 0, right? So upper triangle U, I say this is more or less, this is 6-dimensional, right? Because all other areas are just 0, right? How about symmetric matrix? Symmetric one. Symmetric one, just because m values, these ones are 6, right? Kim Myung-jin, can you understand it? Just it's only 6-dimensional, right? How about U intersection of S? What is it? Upper triangular intersection by symmetric. This is diagonal, right? What's the diagonal matrix? What's the dimension? We have only 3 dimensions, right? 3, right? U is a subspace or not? 박창호, is U is subspace? 이영경, what's the condition for subspace? Because that's why I tried to apply this concept several different cases, right? Subspace is set, indicate this is U, right? I pick any 2 elements there, then combining linearly, do they belong here? Let's say C U1 plus D U2, still this is upper triangular? 박창호. Then closed, right? It's obviously this is upper triangular matrix, then the upper triangular when you combine them, still is upper triangular, right? It's a closed subspace, right? How about symmetric? Like S2, this is also symmetric, right? Symmetric matrix, you combine them linearly, they're symmetric. That's why we just call them upper space. How about diagonal? Diagonal 1, diagonal 2. This is, how about this? This is also diagonal, right? I'm going to stop here rather than discussing this one. Have you learned about this differential equation? Let me try to do this because you have you seen this kind of equation in calculus? Do you know what this means, right? Yeah. Yeah. Just we differentiate y twice, right? By x, right? Then plus y equals 0. This we call differential equations. We try to solve them. Okay? Let's just try to understand the concept, okay? Then when you solve this problem, do you know y cosine x, when you differentiate cosine x, what's the result? Minus cosine x, minus sin x, right? Then how about when you differentiate twice, what's the bill? Then is this a solution for this? How about sin x? Sin x is also solution over there? 박한설, can you follow? Okay, this at least we understand this one is okay. Differentiate y twice by x, right? Then plus y equals 0. We try to solve this equation, okay? This is almost like we try to solve ax equals 0. Okay? Then says if y equals cosine x, then when you substitute this whatever, right? Then this is one of the answer, right? The y sin x is also another answer. So when you combine them linearly, there's also another answer, right? Okay? This is almost like solving ax equals 0. We had one special solution, then another special solution, right? Then combine them linearly. So this is, cosine x, sin x, this is almost basis of null spaces. What I'm trying to say is this concept is applicable in solving differential equation. It means we can use linear algebra to solve differential equation actually. That's the way we do. Okay? Then just think about it. You don't have to understand all this, how it works, but at least try to understand the concept. Okay? Now, previously I solved whatever this equals 0. Now I try to solve this fx is not 0. Okay? Then complete solution is this is special solution plus particular solution. This is almost identical when you solve linear equation, right? All same thing. So once you understand that, it's almost same. This is just this basis of this null space. Combine them, the special solution. This is a particular solution. Okay? 지영탁, okay? Then, how can I solve this one? In case of B, then, how about the y is b plus this? When you differentiation twice, then this term, okay, they will be cancelled out. B's remain. Then b plus whatever this null solution seems to be solution, right? This is a particular solution. This is space on null space. Combine them. This is a total solution. So this is concept I try to introduce. So this same approach is used many different cases. It's almost same. Okay? In the case of fx is ax plus b, this is also same. I can solve them. Also, this is also another particular solution. Then the ax plus b is particular solution. Then there's the one. Also, you can solve whatever this one. Then you can solve all these different cases. We can solve the solution. So basically what I'm saying is this differential equations is completely different from linear algebra. But when you follow the way they solve, it's almost identical with the way we solve the linear equation, right? It's not much different. So once you understand this, you should be able to understand how to solve linear differential equations in many cases. That's all I'm trying to deliver today. 오케이. 또 한국말로 해볼게요. 이게 제가 지금 이제 아까 우리 ax equal b를 솔브하기 위해서 여러 가지 했잖아요, 그죠? 그러니까 ax equal b를 솔브하기 위해서 ax equal 0를 구해서 뭐 어쩌고 저쩌고 이런 방법이 비슷한 어프로치가 보니까 여기에 쓰이는 게 뿐만 아니라 좀 다른 경우에도 굉장히 많이 쓰이잖아요. 그죠? 그래서 어프로치가 보면 almost identical. 그래서 내가 계속 얘기하는 게 그냥 따라가는 것보다 그 컨셉을 이해하는 게 굉장히 중요하다 이거예요. 새로운 문제를 맞더라도 저기서 이런 식으로 했으니까 그거랑 비슷하게 나도 이런 어프로치 저기 택하면 되겠네. 지형태 그런 감을 잡아야 되는 거지. 그죠? 무슨 얘기인지 알겠어요? 그냥 요 경우 이렇게 풀어라. 그래서 충분하지 않다고 새로운 경우를 만났을 때는 이런 경우 이렇게 풀더라. 저런 경우 이렇게 풀더라. 그런 어프로치 나도 여기서 택하면 될까? 그래서 컨셉이 중요한 거예요. 예? 그래서 내가 똑같은 거 갖고 자꾸 다른 경우를 예를 들면서도 뭐 미분 방정식, 뭐 그냥 펑션, 뭐 리니어 이퀘이션, 뭐 비슷하네. 그러면 사실 하나를 배워서 여러 번 쓸 수 있는 그런 개념에서 자꾸 얘기하는 거고 그냥 수식을 따라가는 것보다도 뭐 싱글러라는 게 어떻게 의미해서 하는 걸 자꾸 여러 가지 예를 들어서 하는데 그래서 여러분이 책을 읽으면서 그 정도 레벨까지 올라가야지 여러 군대 가도 안 까먹지. 예, 그렇지 않고 그냥 따라만 가면은 군대 가면 다 까먹고 리셋돼서 와요. 예? 그게 이거를 이해해서 자기 걸 만들어야 되거든. 그래서 이게 개념적인 이해하고 근본적으로 하려는 걸 여러 방면에서 여러분이 이렇게 집어넣어야 돼. 그래야지 새로운 문제가 나와도 굉장히 아마 금요일날 시험을 보면 좀 당황할지도 몰라요. 왜냐면 여러분들 지금까지 그냥 문제 풀이만 주로 해봤거든요. 근데 문제 풀이가 아니라 개념을 갖고 진짜 어플라이 해야 되는데 내가 알기로는 우린 그런 데 하면 완전 쥐약이거든. 학생들이. 근데 그런 훈련을 굉장히 해봐야 된다고. 오늘 강의 열로 끝날게요.